Next up, we have 3 panels on HVAC control, which are cooling, the construction method, and the heat pump heat source. So for cooling, the only option that we have by default available in the tool is specify whether the entire district is being actively cooled or not. This has to do with the implementation intricacies of the Excel, but basically it's not easily possible to model some parts being cooled of the district and some parts not. What you can do always is once calculate the district with cooling, active cooling, and the other time without active cooling, and then in the results approximate a partial cooling of the district by post-processing the results. The active cooling system is always assumed to be a heat pump system, either decentralized fan coil heat systems or with a centralized heat pump that is later specified by the heat pump heat source here. Now, the operating temperatures can be changed, but by default we're using a conditioned indoor temperature of maximum 26 degrees Celsius, and if we use flexible HVAC operation, then it can even drop down to 24 degrees. But by default, the set point temperature for the cooling system is 26 degrees. Next up is a parameter of construction method. You might think, why is that in here? Well, the reason is because the type of construction indicates how much thermal energy can be stored in the building mass. So if we have a very heavy construction, such as reinforced concrete or brick construction, then we have a typically higher specific effective heat capacity than we have for hybrid or even light constructions. Typically, existing buildings use a heavy or hybrid system, and lighter construction methods are used for smaller buildings and newer buildings, but this of course depends very much on the district at hand. You can see that these 3 options result in the important aspect here is the watt-hours per square meter in Kelvin specific effective heat capacity that is derived from this. Now, if you know these values, you can provide them in the mask here, but otherwise just use the construction method that seems most appropriate for you. I should add that this is only relevant if you are using flexibility of the heating and cooling system in the district. If you're not using flexibility options, then this only has the effect of basically dampening the effects of outdoor temperature variations. So the higher the fluctuations, the higher the building mass, the lower the fluctuations in indoor temperature will be. Think of a cathedral or church, for example, which has a very high building mass and is therefore very slow to react to outdoor temperature changes, which is why it is cooler in the summer than the outdoor. It heats much more slowly, and the opposite is true in winter. And then thirdly is the heat source for the heat pump system. So by default, the tool is assuming to be providing the heat and cooling of the district with a heat pump system. And heat pumps typically need a source of heat, ambient heat, and there's 3 main options that can be supplied here. The first is the most common version, especially in decentralized versions of heat pumps, which is ambient air. So here the air is used as a heat source to be pumped into the building. The ambient air is the first option. Then we have also ground boreholes, which means drilling 100 to 200, even sometimes 300, but mostly 100 to 200 meter long holes into the ground, filling them with concrete and running some form of water system through it. The water is being heated by the ground to around 15 degrees Celsius all year round, and this 15-degree hot or cold water can then be used as a source for the heat pump. And the other option, the third option, is using groundwater, which is using water from a well in the building as a heat source. The difference in these systems can be expressed as the seasonal coefficient of performance, which means how much heat or cooling energy we get from each supplied electricity unit. So here you can see that ambient air has the lowest seasonal coefficient of performance. So for 1 kilowatt hour of electricity supplied to the heat pump, we get 3.5 kilowatt hours of heat that we can use in the building to heat it, and for cooling we get 4 kilowatt hours. This has to do with the relatively low heat capacity of air. Air is very light and not consisting of many molecules, so it cannot store heat as efficiently as water. So this is why you see when you go to the water-based solution, which is either boreholes, which you can do pretty much anywhere, or groundwater, which you need a water aquifer that you can access from a well. Both of these have a much higher seasonal coefficient of performance, with 4.25 to 4.5 for cooling with ground boreholes, and with groundwater it's even higher, with 4.7 and 4.8. Now, these are just very indicative values. They can change varying on the soil conditions. Some ground is not suitable and as conductive as other ground, so there is less heat possible to be extracted. Now, this needs to be, of course, all of these assumptions need to be checked with your local project specifics, but as a first rough indication, these values are sound and can be used to model the district. One note on the technicality of these systems. Ambient air, I think you all are familiar with the white boxes hanging from windows or standing on top of buildings. So these air heat pump sources need some space for the equipment which is outdoor, which has access to the ambient air. And it is important to remember and keep in mind that supplying the heating as well for buildings and not just cooling individual rooms actually requires quite a lot of equipment. So typically 10 to 20% of the roof should be reserved for these systems, appliances, which then may reduce the amount of photovoltaics that is potentially applicable to the roof. So keep that in mind, that for the ambient air system you need some space somewhere, and also they can be quite noisy, so there might be a comfort issue there. The ground boreholes, if you have they basically, as I said, are holes of 100 to 200 meters length drilled into the ground, typically in a distance of 6 meters from one another. So if you have an existing district, the machinery for drilling needs to be possible to drill into the ground. So the spaces to drill into need to be accessible by relatively heavy machinery. And typically you need a couple of hundred to 1,000 of these holes drilled into the ground for supplying a decent sized district. So they typically need to be spaced apart in a distance of around or at least 6 meters. Otherwise the cooling of the ground is too large. So for new constructions with a low heat loss, it is no problem to have enough area to be drilled into. But for existing districts with a very high heating demand and not enough space for these drillings, it can be a little bit of a challenge. Other than that, it is possible to use also free green spaces and even sometimes public spaces to locate these drillings. And for new constructions, these ground holes can be drilled underneath the new building foundations and then connected via a heat pump in the basement. Another important aspect of these ground boreholes is that when we are using the ground heat source for heating, we're basically pumping the heat that is stored in the earth. In winter, we're pumping it up into the buildings. And by doing so, we extract the heat from the ground. And that means that over time, if we're doing this year after year, the ground will actually gradually cool down. And if we do this too much with a very high heat extraction rate, then it can even lead to the situation that the ground will freeze. So once it reaches 0 degrees Celsius, it will freeze, which then means that we cannot pump any liquid through the boreholes anymore, and the whole system needs to halt. Now, this is a situation that practitioners now are very keen to avoid, because it is very costly to then defreeze this system by adding freezing agents into the liquid cycle. So one way to avoid this is to make sure that the heat balance that is extracted from the ground is actually in balance. What does that mean? That means that the energy and the heat that you are extracting from the ground in winter, you should also supply in summer back into the building. And this is where the heating and cooling effects of the heat pump solution is very beneficial, because if you have a cooling demand in summer, you can use the energy that you extract from the rooms to cool them and pump them back into the ground and reheating the ground so that you can then in the next winter use the heat again. So basically you're using the Earth as a seasonal storage of thermal energy and using the energy in winter to cool, in winter to heat, and in summer to cool. Now, this only works if the balance of heating demand and cooling demand is roughly in equilibrium. If you have the same heating demand and cooling demand, then this evens out and you can leave the temperature of the ground relatively stable. So this needs to be checked, and if you have a higher heating demand than a cooling demand, then sometimes additional measures to regenerate the ground temperature are required. Some options include directly using solar thermal installations to provide hot water into the ground in summer, or now there are some other options of using, for example, pipes in the concrete of urban heat islands, intersections, and other roads to provide additional heat sources in summer to regenerate the ground below. And one final remark on the groundwater heat pump, which is a very attractive option, but it is a little more situational because the ground boreholes you can pretty much drill everywhere, depending on ground connectivity, but groundwater is very much dependent on the water level of the groundwater, how high it is, how deep the well needs to be, and it is also typically important to check that you don't cool down the groundwater too much, especially once the groundwater drifts. Typically there is a drift of groundwater, and if it drifts too much into a neighboring plot, this might be an issue with your local administrative bodies. So this needs to be checked situationally as well.